Dear physics students, hello, welcome again. This is A.4 and Rubber Duck Physics. We have talked about how objects can rotate around a fixed axis, actually quite long, and the energy they store in that rotation. What happens when an object is both rotating and moving forward? This brings us to the concept of rolling motion without slipping. Before we dive into rolling, let's quickly recap two key ideas. Rotational motion is when an object spins around a fixed axis, like a potter's wheel rotating. Linear motion is, however, when an object moves in a straight line, like a car driving down the road, not considering its wheels, but the car itself as a whole. When an object rolls without slipping, it's doing both at the same time. It's rotating and moving linearly. The description of moving with slipping is much more complicated and not part of the DP syllabus. So how do these two motions interact, and what does that mean for the object's speed and energy? Rolling without slipping means that the point of contact between the object and the surface doesn't slide. In other words, when a wheel rolls, the point touching the ground is momentarily at rest relative to the ground. Imagine a bike tire. As the tire rolls, each point on the surface briefly touches the ground and then lifts off. If it's rolling without slipping, the point of contact isn't sliding along the road. It's sticking, then lifting. To understand rolling, we need to see how it's different from rotation around a fixed axis. In case of fixed axis rotation, the center of the object is stationary, and every point on the object rotates around this center, like a wheel spinning in place. However, in rolling motion, the object is both rotating and moving forward, so its center is also moving in a straight line, like a wheel on a bike being ridden. It's essential to understand that although we have equations like V equals omega times r to describe rolling motion, which might look familiar from circular motion already, their meaning is different here. We'll explain this further as we go along. When an object is rolling without slipping, there is a connection between its linear velocity and its angular velocity. We use the equation V equals omega times r. But it's important to note that the V here refers to the linear velocity of the object's center, and r is the radius of the rolling object. Earlier, when we talked about V equals omega times r, we were referring to the velocity of a point on a rotating object, usually on its outside or edge. Now, when rolling, we are using an equation that looks the same, but it's describing how the center of the object moves in a straight line. The meaning is different because we are combining linear and rotational motion. Think about a rolling tire. The center of the tire is moving forward at a speed v, while the tire is also rotating around that center. These two motions are linked, but we are talking about the linear motion of the whole object now, not just a point on it. Just like we have a relationship between linear velocity and angular velocity, we also have one for linear acceleration and angular acceleration. A equals alpha times r. Here a is the linear acceleration of the object's center and alpha is the angular acceleration. But again, don't mix this up with the acceleration of a point on the object's edge. That describes details of accelerating circular motion. The acceleration of the center is what we are focusing on here because it helps us understand how the object moves overall, not just how it spins. Let's look at a few examples of rolling without slipping to make this more concrete. Number 1, bike tires. When you are cycling, the tires are rolling without slipping. If they slip, you lose traction. Number 2, a ball rolling across the floor. The ball spins and moves forward, with the point of contact momentarily at rest. Since rolling objects are both rotating and translating, they have two types of kinetic energy. Translational kinetic energy, due to the motion of the center, the whole object, and rotational kinetic energy due to spinning around the center. The total kinetic energy of a rolling object is E kinetic equals 1/2 times m times v squared plus 1/2 times I times omega squared. Here v is the speed of the center and omega is the angular velocity. Since V equals omega times r, we could also substitute into V, and after some rearrangement, express the total kinetic energy like this. E kinetic equals 1/2 times bracket m times r squared plus I bracket times omega squared. This can help us understand how linear and rotational motion contribute to the total kinetic energy of the object. In the examples we have seen in this video, on horizontal ground, we mostly dealt with uniform rolling motion. Accelerating or decelerating that motion would often require a complicated mechanism, like pedals and chains on a bike, or at least brake pads pushing against a wheel, and to describe even the latter would involve complex torque calculations. But there is a much simpler way to make a rolling object speed up or slow down by letting it travel on an inclined path. In this case, gravity acts directly at the center of mass of the object, creating a steady torque that naturally accelerates or decelerates the rolling. In our next video, we'll explore how rolling objects behave on inclines and see how gravity's steady torque affects their motion. Stay tuned for a closer look at rolling on slopes. To sum up this video, rolling without slipping on horizontal ground is when an object is both rotating and moving forward, with the point of contact at rest relative to the ground. We have seen how equations like V equals omega times r look similar to what we have seen before, but now describe a different kind of motion. Rolling objects also have two types of kinetic energy. Understanding this concept will make it easier to see what happens when rolling objects deal with inclines. Stay tuned, and we'll explore that next. Enjoying these lessons? For more in-depth one-on-one tutoring or in small groups, I am available online for IB DP Physics or A-level Physics and Maths or AP Physics students. You can get my contact info from the Rubber Duck Physics YouTube channel description. Just make sure you are using a web browser. Reach out to arrange a trial lesson. Thank you for watching the video. See you next time.